Oops. Homework, pretty good job. Union and intersection was the most missed off the first try, 52%, but that's half of you guys. The Mac or PC, one of the multiple choices was number 3. Like I said, guys, the multiple choice ones are more like what you're going to see on the test. Okay, just kind of always remember that. I don't know why I've gotten into doing this. Not good, I guess. What is the probability of getting craps or an even? And so what you need to do is go through this little table right here and it says if it's 2, 3, or 12, it's craps. So here's a 2, 3, 12, or an even 4, 6, 8, 10. So you should just add those up. That's 1, that's 2, 3, 4, 5, 6, 11, 16, 17, 18, 19, 20. 20 out of the 36 should be. Okay with that? So that's one that you're going to see one very similar to that on the test. Again, this is previous years, but I haven't changed a whole lot of them. It's going to show you a probability model, and it's going to drop one of the probabilities. So like you can't see one of the probabilities. But if it's a probability model, you know that they all add up to 1. And so whichever one you're missing, you basically subtract from 1 to find out that one that's missing. Y'all okay with that? And then it's going to ask you some questions like, what is the probability of? And it doesn't have near this many. It has like 4. Y'all okay with that? So anyway, make sure, like I said, most of this stuff, I kind of understand why you're going to miss it, because you're learning, right? You're learning. And so I didn't think that was too bad. Anybody have something that they stick in their head besides that number 16 or 17 from that 5-1?
I forgot what it was about, but it's kind of confusing.
Is number 18? Whoop, I gotta go to a arrow. You see it? Where'd it go? Oh, there it is. Dogs and cats revisited. Oops, I need to clear all that. Oh, here we go. So you'll see this one today, actually, the same question. Different part here. Are dogs and cats using that? Okay, so they want, here we go. Dog, not a dog. Cat, not a cat. Total, 40% own dog, 0.4. That must mean 0.6 don't. 32 own a cat. 32, this must mean 68 don't. And then 18 own both. And so if that's 18, this must be 0.22. This must be 0.1, 8, 9, 10, 11, 12, 4. 1, 2, 3, 0.46, 4, 5. Yeah, that works. Using the events dog owns a dog and C owns a cat, find the probability of D and not C. Don't use equations. That's only for DRINs. Some of you knuckleheads I know will use equations, but just make the table. I'm telling you. Yep. It takes a little while to make them. Just find out the answer to one, but you get 2.5 minutes per question. So you'll have time. I see you sneaking in. Knuckleheads. Don't Vaughn be both of y'all in trouble. Oops, sorry. Say your name over the internet. Don't look at me like that.
How's it going?
That's better. That's how that look was. You can open your eyes and see. It's early, I know. Need coffee? Is that what it is? Mm-hmm. Stunt your growth. I don't know if that's true or not. Good? Anything else? Y'all okay, kind of? More practice today with some different type questions. So here we go with 5.3. Again, I apologize. I changed them up a lot, but I think I simplified it enough to where I'm going to give you all the information you need to know. Let's go to, I got to get to the beginning though. And I say that because yesterday was pretty busy. So today is conditional probability and independence. Last two things. These type of questions are, I don't want to say make it more difficult, but it sure makes it a little bit more tricky. Not the independence. Independence is pretty simple. The conditional is not too bad. It's when they just throw it all in together. Okay? It's when they throw it all in together. So here we go with conditional probability and independence. All right. I'm going to return back to my gender and ear piercing. Okay? Let's go back to my gender and ear piercing. You'll remember that we have a male or a female, and they either had their ears pierced or they didn't have their ears pierced. It's really nice when y'all go back-to-back days because it was just yesterday. You don't have to think real hard. Okay? We know that the probability of being a male is pretty easy. That's 90 out of the 178. The probability of having a pierced ear was 103 out of 178. Okay? The probability of A and B was 19 out of the 178. And I think that we said the probability of A or B was the 71, the 19, and the 84. Remember, I told you there's three ways to find that. You can add the 71, add the 19, add the 84. You probably saw on your homework that that's sometimes the way they'll do it. They'll show those three being added. They'll show two of them being added, these two being added and subtracted. They will, let me rephrase that. I don't think they'll ever show one minus that to show it. But just understand, okay? A lot of times they show the work to get the answer, not necessarily the answer. They'll do that a lot, okay? So that was that one right there, okay? Now, conditional probability today. What they're going to do is they're going to set a certain condition, a certain known condition. Let's go and turn our attention to some other interesting probability questions. If we know that a randomly selected student has a pierced ear, okay, so we assume already that they have a pierced ear. If they already have a pierced ear, guys, we're no longer talking about these, whoops, I need a pencil. We're not talking about these 178 cats. We're only talking about those 103 cats, okay? So that's what they're going to do today. They're going to tell you, hey, we know this already happens, okay? What's the probability that they are male? Well, in order to be a male, I don't care about these 71 here because they aren't have anything to do with having a pierced ear. So all I'm care about is those 19 cats. And so the answer to that particular question would just simply be 19 out of the 103. Those conditions are going to change your denominators. Those conditions are going to change your, yesterday, I think every one of your denominators was that bottom right. Okay? So that would be the 19 out of the 103. Second question, if we know that a randomly selected student is a male, okay, I don't even care about this information anymore. And that's sometimes what I'll do with my tables. I'll just mark that stuff out because this is all I care about. That's all I care about. What's the probability they have a pierced ear? That's that same 19 cats, but now instead of being out of the 103, it's out of the 90. Okay with that? So that's what they're going to, that's what they're going to do is they're going to give you some kind of a certain condition, and then they're going to say, what's the probability of this happening out of that condition? Okay? Boom, boom, boom. These two questions sound alike, but they're actually very different. Yeah, and that's why you have to be really careful about it. If we know that a randomly selected student is a male, that's where I'm going to stop. That's called my given. Kind of like the old, was it proofs in geometry? Given this, prove this. Well, we don't have to prove anything. We're given this. Now what's the probability of this? Okay? Each of these problems, an example of a conditional probability. These names comes from the fact we're trying to find the probability that one event will happen under the condition that some other event has already known to occur. So let me give you that definition, conditional probability, okay? Conditional probability. It's the probability that takes into account a given condition has occurred. A given condition has occurred. And they'll tell you what it is. Given this, or we know that this, or out of these people. Okay, that's what they'll do when a conditional, and there's a bunch of ways they'll say it. I'm going to try to cover most of them today in notes, but then you'll see several of them with homework. okay, under the given condition. So we got conditional probability. They're going to give you some condition. The probability takes into account some given condition. And those two examples that we just did were conditional probabilities. And you just have to recognize that. You have to recognize it when you do these. Okay? All right, here we go. We're good? Good. Boom. It's the notation. I'm sorry. That's a very important, okay? So they're going to say the probability of B, and they're just going to do a big old gash, a big old line, okay? That's the given. Given that A has occurred. Given that A has occurred. The probability of B, given that A has occurred. So that's my given that. I kind of treat it my denominator, right? This is like a fraction, kind of. Given that A has occurred, that's my bottom, that's my denominator, okay? So A given that, and they'll typically write it just like that. And I would expect you guys to, we don't want to write given that every single time, we just want to write that line, okay? Beautiful. Red given that, okay? So can we restate this question using notation? You kind of have to know this notation. If we know that a randomly selected student has a pierced ear, they have a pierced ear. Okay? Have. And I think they put that as B or A. And that's what they'll do again. Kind of remember that they'll give you a capital letter for something so we don't have to write out have a pierced ear. But even then, you don't have to write out everything. If it's completely understood that this is have a pierced ear, and then what's the probability that they are male? So male would go there. Okay? And that's perfectly fine. You don't have to write them all the way out. And like I said, most time they're going to give you those capital letters. Okay, soak that in. Everybody good? Beautiful, beautiful, beautiful. There it is. You can kind of see it in non-hieroglyphics. Again, I don't write pierced ear. You just write pierced and you're okay. Or has or whatever. Okay? If we know that a randomly selected student is a male, that's given that they are male. Given that they are male. What's the probability that they have a pierced ear? Okay? Everybody good? Beautiful. Beautiful. So it's important to know how to write it, but it's also important to find the probability. In 1912, a luxury liner Titanic, on its first voyage across the Atlantic, struck an iceberg and sank. Some passengers got off the ship in lifeboats, but many died. Supposedly randomly select one of the adult passengers from the Titanic. Define F as a first-class passenger, S is survived, T is a third-class passenger. I want you to take a note to this table first. This is one of those tables that's not a two by two. It's actually 3 by 2. And sometimes that happens, okay? I mentioned that maybe you might see one that has like juniors, seniors, sophomores, or whatever it might be. You might see 3. Everything we've done or everything you did last night. Hola, thank you. Stay. Everything, like I said, everything we did yesterday was 2 by 2. Talk to me.
So what was the value? Because it was like our variable and then our variable C.
So it's still the variable. Is that right? Because this is still the class of travel. So it happened to just be, instead of just 2 classes, like it was dog, not a dog. You can't do it that way. Like I said, you have to do it like a class. Like if I'm just talking juniors and seniors, that's all we have, juniors or seniors. But if we have 3 classes, it might be juniors or seniors or sophomores. It has to encompass everybody. It has to encompass the sample space. Is that helping you some? If we added like our school, we have the freshmen, so we would actually have 4 columns. We'd have the freshmen, sophomores, juniors, and seniors. Okay, it has to fit one of those categories. You can't add. Who else? Quit being late. I'm okay. Lucky I'm in a good mood last night. Yeah. Okay. You good? All right. So here's my events. F is first class. S is survived. T is third class. Again, they're just trying to shorten up things so I don't have to write everything out. They want to find the probability of T, and some of you guys may not be able to see that. That's why I love these boards so much, as they are so tall. They want to find the probability of T/S. So that's given S, given S. So given that they survived, I'm only talking about those cats right there. I don't even care about these guys, and I don't care about these guys. All right? And then they said T, and T is what? Third class. So the probability that they're third class and they survived, and we simply just need to put 151 over 442. And if you want to, turn that to a decimal. If you don't want to turn that to a decimal, then don't. Question? Yes, ma'am.
So like, if this was on a test, would you need to be like circling and
That's what I would do. If they give you the table, that's the one I know I've tried to instill in you guys. You got to have work, can't have naked answers. As long as you have this, they're okay. They don't want just the decimal by itself. And that's why I kind of emphasize this fraction. If this was a test, and I would go ahead and just do that, just to kind of help me a little bit, just to make sure. But yeah, that's fine.
if you want the decimal?
They don't necessarily want it. They don't want just a decimal. Okay, fair? I turn all mine to decimals just out of habit. But they don't really care. That's the answer. If you got that, they'll accept it. And then the decimal, if you have the decimal, it better be that decimal. Fair? Great question. Yes, ma'am.
Do you have to like simplify the fraction?
No, ma'am. You do not. You do not. When previous test, I would ask one just simple like this, like, can you read the table, pretty much? And I looked for that answer. And if I saw that and I saw other things, then I had to check it just to make sure it was right. But if I saw that and that's all I saw, we're good. Because that's all the rubric showed. Fair enough? If you saw just a decimal, that was -1 because it didn't have this. Okay? If you got the decimal wrong, it's -1. Okay. Beautiful. Boom, boom, boom. There that answer is. Interpret this value in the context. And again, they would just basically want to say, what does this mean? And that's the probability. Given that the person survived, the probability that they were third class is around 34%. Meaning it's not the greatest of chances to be third class and survived, because the third class was way down low and it took them forever to get up. First class had a higher chance of survival. I think that's their next one. Given that a randomly chosen person survived, there's about a 34% chance that he or she was a third class passenger. So again, you're just kind of writing this in words. Just given that they survived, given that a person survived, there was a 34% chance that they were a third class passenger. Okay? Good enough. Interpretation is very important. Make sure you understand what that says, not necessarily how to do it as much. Given that the person, now they're going to ask me another question. Given that the chosen person is not first class. What was first class? Was that an F? How about this? F complement. Not first class. What's the probability that he or she survived? Not first class, he or she survived. Beautiful. So not first class, well, those 319 are first class. I don't want those 319. I want the 261 and the 627. So I guess I need to add those two cats right there to get my denominator. Say again? Given that they're not a first class passenger.
So is it out of the classes or out of the
It's out, given that they're not a first class. Good? I know I'm going a little fast. Y'all okay? Everybody okay? So given that they're not first class, so not these guys and not the totals, we want those cats. What's the probability that they survived? Survived. So there's my numerator. And so this particular one, to show my work, I would show 94 plus 151 over 261 plus 627. And I'd use my little calculator and tell me what those two numbers equal. Good enough? Click. 94 plus 251. I don't guess I wrote anything else. Look, their notation looks just like mine. Oh, amazing how that works. Again, out of habit, I turn that into decimals just because I kind of want to see what that is as a decimal. But if they don't ask, don't worry about There is a formula for conditional probabilities. It's on your formula sheet. I don't think you'll use it very much. However, that formula is there, and it says this: the probability of A given B. Well, it's the intersection. It's the intersection of A and B. It's whatever that intersection is, over the probability of B. Okay, given B, that's the denominator. It's the intersection of those two. Okay, it's the intersection of those two. Again, you won't use it a whole lot because again, I'm forcing you guys pretty much to do tables. Do it how you want. Some of you guys will use the formula. It's fine. It works. It's harder. Let's go back real quick. Oh, boom, right here. This was the intersection. That's my numerator over the given. Okay, just to kind of show you what it is on the formula. So it's the intersection A and B over B. Okay, beautiful. Again, you may or may not use it. If you ever need it, it's on your formula sheet. There's two of these on the formula sheet. This one and the addition rule, the general addition rule. Those are the two that are on your formula sheet. You good? Golly. You guys are so awesome. You make me go home every day happy. Some days you don't. Some days I get ticked. Not really at you guys, though. You guys are awesome because you guys are half asleep. You can write statements like the probability of A given B if A and B are clearly defined. I've kind of mentioned this too. Otherwise, it's probably easier to use contextual labels like P, I given F, like Instagram and Facebook. But it's okay to use I and F if it's so obvious that one of them's Instagram and the other one's Facebook. We were trying to use blue and orange M&Ms, but I really couldn't do B because there was also a brown. But you could do a BL and an O. Okay, just to kind of shorten you guys up. You don't have to be so darn specific that you need to make sure you write down and make sure you can abbreviate as long as it's easily understood. So that's what they're telling you right here. We got in a school, 60% of the students like Cheez-Its. That means 40% are stupid. Better to remain silent, and I assume you're stupid, than to open your mouth and remove all the doubt. He was trying to say something about them other ones. All right, anyway, here we go. 60% like Cheez-Its. Among those who like Cheez-Its, 70% also like pretzels. Among those who did not like Cheez-Its, 20% like pretzels. What's the probability that a student of Cheez-Its like pretzels? Very, very common question. I'm going to go to this thing right here, and I'm going to do this, and I'm going to do this, and I'm going to do this, and I'm going to tic-tac-toe this bad boy, and we're going to draw some lines here, and we're going to make a nice pretty table so that I can get these numbers in something I can see. And the very first thing it says 60% like Cheez-Its. So I'm going to bet one of these is Cheez-Its, and I can put it here, I can put it here, I can put it here, I can put it here. I don't put it in the totals. And I put it up there because that's just a habit I do. The very first one, I put a Cheez-It right there, and this must be a don't like Cheez-It. And it says 60% like these bad boys, so it must mean 40% don't, and I'm going to put a 1 right there. And if you don't like decimals, they used to call them hypothetical 1,000 tables or 100 tables. And so you can turn that to 100 and 60 and 40, but who cares? I think it's easier just to leave them ones, and then you got your decimal answers. Okay. Now, this is the trick. Among those who like Cheez-Its, 70% like pretzels. That's not 70% of the total. That's 70% of these cats. So I got a pretzels and I got a non-pretzel, but that's not 70%. That's the first thing we got to make sure we read when we see this. This is not 70%. In fact, it's impossible to be 70% because there's no way for that to be a 7 and that to be a 6. So that's another helpful clue by making tables. Because if you just use formulas, you don't see that kind of uh-ohs. So the 70% of these cats like pretzels. So this number right here is 0.42 because that's 70% of 60. And if you don't know, you do 0.6 times 0.7 and you hit enter and it's going to give you a 0.42. And now if that's 0.42, this is 0.18. Now, I still can't finish the rest of my table, but hopefully they gave me something else. And they did. Among those who do not like Cheez-Its, 20% like pretzels. So that's these cats right here that don't like Cheez-Its, these idiots right here that have no common sense whatsoever. They're just complete dummies, stupids, idiots that just shouldn't be alive. I probably went too far then. Sorry. So these 40% here, 20% of those cats, which is 20% of 4 is that 0.08, right? Again, you got these nice little calculators that will give you that answer. And so if that's 0.08, this has to be 0.32. And now I can make this 0.5, and I can make that, well, that has to be 0.5. And now I finished up my table. And it says, what is that? What is the probability? So I'm going to go over here and I'm going to say probability, okay, that a student who likes Cheez-Its, sorry, that's bad. I didn't read it rest of the way. Go away. There you go. Given that they like pretzels, likes Cheez-Its, given that they like pretzels. And so that they like pretzels is 0.5 on the bottom, and like Cheez-Its is the 0.42 on top. And now that one I would for sure turn into a decimal. I would not leave that one as a fraction. Okay? I know that's way low for you guys back there in the back. Good? I know, that question wasn't on your paper. I made it up yesterday. Thought it was great. Good? Okay. If you can do that, you're pretty good with conditional probabilities. Okay? Next thing we need to talk about is independence. Independent events. If knowing that one event happens does not affect the ability for the other one, or does not affect the probability of the second. If knowing one event happens or has occurred does not change the probability of the second. They are independent events. They are independent events. Some of them is really, really common sense. For instance, if I'm going to flip a coin and roll a die, those are independent events. It has nothing to do with what I get on the first one as what I'm going to get on the second one. If I flip a coin, that has no determination of what I'm going to get on my die. Those are independent events. Okay? So knowing that something has occurred doesn't affect the other one. A lot of times they'll say, assume the following are independent events. Or they'll give you some type of big old scenario and they'll say, assume they're independent. And so if you know they're independent, that's good. Sometimes they'll ask you, are they independent? And that's probably the harder question of the two. And so that's what we need to spend a little bit of time on today to make sure you understand if they are independent. Okay, definition good? Don't put that yet. Don't put that. Don't put that. Don't put that. Don't put that. I think that's going to confuse you more. I'll go back to it, but don't put it yet. All right, so we're back to my males and pierced ears. Okay, back to my males and my pierced ears. Click. Suppose the chosen student is male. We can see from the two-way table that the probability of being a pierced ear, given that they're male, is 19 out of 90. Okay, we just calculated that at the beginning of class. Okay, so soak that in. That's the probability of, given that they're male, the probability that they have an ear pierced. Okay, suppose that the given female or the chosen student is female. So we're chosen from the female, given I'm sorry, given that they're female, the probability that they have a pierced ear is 84 out of 88. Good enough with that. So just a second ago, we did, where we at? We did 19 out of 90. Now we're going to do 84 out of 88. And I look at 19 out of 90, which I notice is 0.211, and then I notice 84 out of 88 is 0.955, completely different probabilities. Knowing their gender changes the probability of them having a pierced ear. Therefore, those are not independent. Knowing something has happened changed the probability of the other event happening. Knowing their gender changed the probability of them having a pierced ear. Good enough with that? Those are not independent. Those are dependent. It depends on what their gender is, whether they have pierced ear or not. Good? Pierced ear male is 0.211. Pierced ear female is 0.579. Those are different. So because those are different, those are dependent events. If those happen to be the same, then it wouldn't matter what their gender was, whether they had a pierced ear or not, wouldn't matter. So we didn't know it. Good? Click. If those were equal, it wouldn't matter knowing their gender if they had a pierced ear or not, then it would be an independent event if they're the same. So what you're looking for, guys, and I hope this helps you. I'm trying, again, this is all different. What you're really looking for is ratios. You're looking for ratios. If 19 over 90 is the same as 84 over 88, is the same as 103 over 178. If any one of those are the same, they're independent events. Yep, yep. Because if this is the same and this is the same, then that one has to be the same. It's okay. I understand. It's good. Good enough for that? Or you can go the other way, right? Red. If that's the same and that's the same, or that's the same. If those are the same, then it wouldn't matter if they had a pierced ear, knowing that they had a pierced ear, what their gender would be. Okay, hit me.
Do they just have to be similar, or like?
They should be really, really close. And what I mean by that, what he's asking, if it's 0.211 and 0.210, now it's gonna be one of those you probably really can't miss it. Fair enough? Because these are really, really close, I'm going to say they're independent. Or because these are a little bit different, I'm going to say they're dependent. And either one of those would be acceptable. Yep.
What about like 0.2 and 0.3?
That's not close enough. They gotta be closer than that. It's gotta be close. Fair enough? Great questions. God, man, I love you guys. See, I'll take this and go to each class. Because I know what you're thinking. That's why you ask good questions. That's why I film you guys. Plus you're first today. Huh? Everybody else okay? Keep going. Click. Knowing that the chosen student is male changes, it greatly reduces the probability that the student has a pierced ear. You don't really care that it reduces or increases. You just care that it's different. Boom. Chose a random SRS of 100 Australian school students who completed a survey, the two-way table. Oh man, they gave me the two-way table. That's really, really, really nice of them. Are the events male and left-handed independent? This is a common question. Male and left-handed independent. In other words, knowing if they're male or knowing that they're left-handed, does that justify the difference in probabilities? So I would go left-handed. Male, knowing that they're male, left-handed. That's 7 out of 46. And again, I would write the probability of male, dadgummit, I do that often. You'll do that often too. Probability given that they're male, left-handed. Okay? That's that fraction right there. Well, is that different knowing if they're female and left-handed? And female, probability of given that they're female left-handed, that is 3 over 54. And so I'll just take my little calculator out and I'll take 7 divided by 46 and I'll take 3 divided by 54. And if those are the same, we would say what? They are independent. If they are different, we're going to say it must depend on something, which we would think it wouldn't be, because I don't think it matters if you're male or female about being left-handed or right-handed. But we need to see. It's 0.152 and 0.056. So out of this sample, it must matter. These are dependent events. Those are dependent events. Knowing if they're male or female out of this group. Okay, out of that group. Because you would think overall, I don't think it would matter. But this is the only information we got to go with it. Because the probabilities are not equal, these events, male and left-handed, are not independent. Knowing that a student is a male increases the probability that they're left-handed. Okay? Knowing that they're male increased the probability of being left-handed. Beautiful. Soak all that in. I'm doing a good job this year. A little praise doesn't hurt. Yeah, so are you guys. Okay, everybody writing? Everybody done writing? No? Okay, right away. Or left. I didn't even plan for that one. That one kind of just happened. What happened? I said right away. And then I said or left. Funny. Y'all know one of my favorite jokes is I ask how you're doing, and they'll say they're all right. I said, you can't be all right. Because if you're all right, nothing's left. If you can have nothing left, then you're not here. Okay. Last thing we need to cover today. Okay. This is the general multiplication rule. General multiplication rule. It says this: 55% of high school athletes participate in an athletic team. So 55% participate on some school athletic team. 6% of these. I don't think this is that difficult, but again, you got to read carefully. 6% of these go on to play college and in the NCAA. What percent of high school play a sport and go on? And all I got to do to those two percentages is multiply them. Because there's 55% that go to high school. Of those, 6% go on to college. So it's of those. Of means multiply. We're just going to take those two cats right there and multiply them. And that's the percent of students in high school that go on to play college. It is tiny. What was it? 3.3%. Pretty small. Okay? Everybody good with that? Let's proceed on that one just a little bit further. No. I'll give it to you. It's on the formula sheet. I don't think you'll use it. Probability of A and B is equal to the probability of A multiplied by the probability of B given that A has happened. Probability of A multiplied by the probability of B given that A has happened. I don't think you'll use it. Now, let me ask you this, though. If the A and B are independent, if A and B are independent, it won't matter if A has happened. It's going to be the probability of A times the probability of B. which is what just happened. That's what we just did. Probability of 0.55 times the probability of 0.06. If this one happened and it doesn't affect it, we'll just multiply the two together. Okay? So roll with that. Yep. If they're independent, then doesn't matter if A has happened or not, it won't change the probability of B, then this will just be the probability of B. Yep. Yes. So this applies independent or dependent. If they're independent, then that's just the probability of B. I'm going, I sometimes think I'm giving you too much, but then I sometimes don't think I'm giving you enough. Here's a way you can prove independence or dependence. If the probability of A given B equals the probability of A. That's one way to prove it. Y'all follow what I'm saying? If the probability of A given B, if that doesn't change the probability of A, in other words, you know if B has happened, if it doesn't change the probability of A, those have to be independent events. They're going to ask you to prove independence, some way, some form, some fashion. I think ratios are the easiest way to prove it. I think ratios, because that goes back to my tables. So if I have my tables made, I can look at ratios and just decide on if they're independent or dependent. But this formula will also prove it. Okay? There's several ways to prove it. All right, here we go. You can or don't have to. I want to show, I remember I told you there's 4 ways to do these. Formulas, tables, Venn diagrams, tree diagrams. Sometimes tree diagrams make it easier. Again, I like to still make tables, but I want to show you a tree diagram just to be sure that you kind of see it. What you do is you start off with some way. You either like Cheez-Its or don't like Cheez-Its. Like Cheez-Its, don't like Cheez-Its. And then you either like pretzels, don't like pretzels. So that's kind of the way the tree works. Some students like trees just as much as tables. You like Cheez-Its. You either like, don't like, 0.6, 0.4. And then of these, that's where it starts to get difficult because coming up with these numbers here, sometimes it's easier, sometimes it's harder. Okay? So, here we go. Shannon hits the snooze button on her alarm 60% of school days. If she hits snooze, there's a 70% probability she makes it to her first class on time. If she doesn't hit snooze and get up right away, there's a 90% chance she makes it on time. It's a great question. Quit hitting snooze. If you want to make a table of this, it's perfectly fine. And you guys, again, I kind of get stuck in this table mode. I just kind of make everything out of tables. She hits it. So she either hits snooze or doesn't hit snooze. C. Nope, doesn't. Does not matter. And then she either is on time or late. Sometimes I like to do on time, late as opposed to on time, not on time. She hits it 60% of the days. She hits 60, she doesn't hit it 40% of the time because you either hit it or you don't hit it. Again, that's where some students will mess up. They'll do the snooze and the late. No, it has to be the snooze, non-snooze, late, not late. On time, not on time. Okay? If she hits it, there's a 70% probability. This looks very similar. In fact, it's exactly similar because this is 0.42. She makes it to her first class on time. So if she hits it, she's on time. And now I can do this, which is 0.18. If she doesn't hit snooze, there's a 90%. So that's a different number. She's a 90%. So this is 0.36 because it's 90% of that 40. And now this is 0.04. We can finish this up by saying 0.78. And we can finish this up with 0.22. And now we can ask you any question we want on this, like what is the probability she makes it to school on time? 78%. We can ask a conditional probability. If she hits snooze, what's the chances she's on time? If she hits snooze, what's the percent she's on time? 42 out of the 0.6. Okay? So that's my table. If you wanted to make a tree diagram from that, you could. Just quickly, I might want to show that. 70% chance she hits snooze, that's a 30% chance. And then from that, we're either late or on time. Late, on time. If, oh, sorry. Thanks. A debate about even showing this, but 6, 4. Okay. If she hits her snooze, then there's a 70% she makes it on time. 0.7 and then 0.3. So you don't have to worry about multiplying it yet. You multiply it over here. But then over here, you have to do addition stuff. I still think the table's a better way to go. But I want to show you that there is other options if you don't like tables. That's the tree diagram. You either hit snooze or you don't hit snooze. You're on time or you're late. You're on time or you're late down here. There's the 60, there's the 70, and there's the 30. There's the 40, there's the 90, there's the 10. And then we got to multiply over here to get me the 0.42, multiply here to get me the 0.18, multiply here to get me the 0.36, and multiply here to give me the 0.04. But you still have to do some additions to find the totals. Because what's the percent they're on time? Well, it's this one and this one. It just works, and I don't know if it's better or worse. I still like the tables, but yes. 0.6, 0.7, 0.6, 0.3. That's okay. It's good. I'm going through it like everybody understands, and I forget this first time you've seen it. Click. Click. What's the probability Shannon hits snooze and is late? So we could go here and see that. Hits snooze and is late. 0.18 out of 0.6. Table, you'd have to do whatever. I don't want to teach it. Click, click, click. Last one. I'm going to show you again one more time of when there's not just a 2x2. Okay? So recently, Harris Interactive reported 20% of millennials, 25% of Generation X, 21% of baby boomers, and 17% of mature. So this is one that you're not going to have just 2. You're going to have 4 across the top or on the side. 4, okay? Because you have 4 different groups. And then it says read more ebooks than print books. So one of your columns ebooks, and then you have print books. Okay with that? And you go along through there, and then you can kind of make the table. So your table looks a lot different for this one than it does all the other ones. Just understand that every once in a while, they'll give you more than just 2, a yes or a no. You could be this one, A, B, or C, or maybe A, B, C, or D in this case. Okay, just kind of recognize that. There they made a tree diagram with it, and that gets really confusing to me more than a table. Beautiful, beautiful, beautiful. I don't want to go through all that. I want you guys, I got to cover this. So all these won't cover any of these kind of questions. When A and B are independent, the probability of B given A, that's what I was going to tell you. That's what I told you. When they're independent, the probability of B given A is equal to the probability of B. Because if they're independent, then the probability of knowing A won't affect the probability of B. So that's a statement right there. Again, we kind of need to know that in order to do these next examples. If A and B are independent, then the probability of A and B is equal to the probability of A times the probability of B. If they're independent. I don't like giving this formula. It's kind of like the mutually exclusive formula for addition. I don't really like giving that one because it only works then. This only works if they're independent. But I kind of mentioned that already. Just kind of, yeah. You need to know that though. I'm going to hit you 2 examples here in just a second that you're going to see. 2 examples you're going to see. Okay, ready? Click, click, click. Diablo Canyon Nuclear Power Plant in California has a warning system that includes a network of sirens. Okay? When the system is tested, individual sirens sometimes fail. That's bad. The sirens operate independently of one another. In other words, if that one fails, it has no bearing on this one failing. Whereas sometimes if that one fails, rest of them fails, like Christmas tree lights. Used to back in the day, if one of those failed, it failed rest of them because it cut the circuit. Now I think they got that fixed. Where the circuit goes through and you can still have a light, and if it goes out, it still completes the circuit. Anyway, that's a me problem. Imagine that you live near Diablo Canyon and there are 2 sirens that I can hear. You might be concerned about probability that both fail, 1 and 2 fail. When the siren system is activated, 5% of the sirens fail, or 5% of the time. What is the probability that both sirens fail? 0.05 times 0.05. Because they're independent, you take the probability of this one not failing and the probability of this one failing and just multiply those 2 together. Good enough? Click, click, click. Pedro drives on the same route to work on Monday through Friday, just like you guys probably drive the same route to work or to school Monday through Friday. His route includes 1 traffic light. Yours probably does not. The probability the light will be green is 0.42, yellow is 0.03, and red is 0.55. And that's not my light because mine is 0.99 red. What is the probability that the light is green on Monday and red on Tuesday? Probability of green on Monday and red on Tuesday. And I think those lights operate independently because I don't think what happens on Monday affects what happens on Tuesday. So I'm going to take the probability of green, which is 0.42, probability of red, which is 0.55, and I'm going to multiply those 2 together. Good enough? Question on your test, very similar to that. Yep. Yep. Sometimes we have to, normally they will say it, but that one there, you have to almost just assume it. But normally they'll say it. I don't want to, how about this? You assume they're dependent unless if you know. I think you're better off assuming they're dependent. Beautiful. What's the probability he finds a red light on Monday through Friday? That's a red and a red and a red and a red and a red, which is 0.55 to the 5th power. Mathematics, good? Red. Point what? 0.53. A 5% chance it's red every day. I still think mine's like 98%. All right, last one. I know I've been through a bunch. Okay. I hate that they throw this one in here, but this one really should be part of next chapter. So bear in mind that you could see this. This is the one, this is the bad one just because they don't give enough examples for it. Many people who visit clinics tested for HIV, the virus that causes AIDS, don't come back to learn their test results. So you got a clinic, they go in to get tested, they don't come back for their results. Clinics now use a rapid HIV test that gives a result while they wait. So they go get the test and then they wait. It's rapid. A clinic in Malawi, for example, uses a rapid test, increased the percentage of clients who learn their test results from 69% to 99%. Because it was rapid, they learned it, more of them learned. The trade-off for that is the rapid tests are less accurate than the slower ones. Applied to people who have HIV antibodies, one rapid test has a probability of 0.004 of producing a false positive. Okay, so now you kind of have to know what a false positive is. A false positive means that they showed it positive, but they didn't have it. So you kind of have to understand what that is. It show they have it, but they didn't really have it. Oh, and they tell you falsely indicated antibiotics are present. If a clinic tests 200 randomly selected people who are free of antibiotics, so they're free of it, what's the probability that at least one of those will occur? This could be a really, really, really hard question because it could be the first one, or it could be the second one, or it could be the third one, or it could be the first and the second, or the first and the second and the third, or that would take forever. But what you're going to assume is they all get it. They all test positive and subtract that from one because that's the only one that doesn't have at least one. Let me say all that again. If you want at least one, it could be the first one, or it could be the second one, or it could be the third one, or it could be the first and the second, or the first and the second and the third and the fourth. The only one that doesn't have at least one is all of them don't have it. So what you're going to do for this particular one, what is the probability that at least one false positive will occur? One false positive will occur. Assume that the test results are independent, and there's where they're going to tell you that they're independent. So rather than take 1,500,000 times, I'm going to take 0.996, which is the complement of getting a false positive. That's the complement of a false positive is the 0.996. I'm going to assume that nobody tested for it. I'm going to assume that nobody tested for it. So that's 0.996 to the 200, which is some big old number, 0.4486. So that's the probability that nobody tested for it. The probability of at least one is the complement of that, which is the 0.5514. So even though there's a very, very small chance of a 0.004 of testing positive, if you don't have it, there's 200 people. And at least one of those 200 testing positive is a 55% chance, which is still half, but that's 200 people. Okay with that? So anytime you see at least one, figure out one minus the probability of none. Figure out the probability of one minus none. Anytime you see at least one, and you will see one of those on the test. You will see one of those on the test. At least one. Then you figure out the probability of none, which is the complement, and subtract it from one. And it turns out to be a pretty easy question if you can know that. Okay, question about that. At least one. Figure out the probability of none and subtract it from one. Beautiful. I hope you can calculate and interpret conditional probabilities. That's what we did at the very beginning. I hope that you can determine if they're independent. That's an issue that some students have, proving independence. Hopefully by me going over those ratios today helps you. Use the general multiplication rule to calculate the probabilities. If they're independent, you just multiply them together and then calculate. Oh, it says use a tree diagram. We don't use tree diagrams. When appropriate, use the multiplication rule for conditional probabilities. Beautiful, beautiful, beautiful. Let me go to arrows. Let me go here, exit, go here.